What if I told you that in October 2017, humanity received its first message from an alien intelligence? Not through radio waves or optical signals, but through something
It sped
far more
up as it was
sophisticated.
leaving the solar system,
Physical object
far
that
more than
arrived from
ordinary
interstellar
comets
space,
do
performed
through
a
our
carefully
solar system in
choreographed dance through our solar system,
2017, and
then
right away
transmitted a
made
response signal
news.
across the cosmic
Elongated
void.
shape made
A
it
signal
an
so powerful, so precisely
the
aimed,
comet known
that it
as
summoned a massive
Oumuamua.
reply nearly 8 years later. In 2017, we discovered Oumuamua, an object
It
unlike
sped
anything
up
we'd
as
ever
it was
seen.
leaving the solar
Thin as a
system.
razor blade, tumbling through space, accelerating in ways that defied gravitational physics. We called it our first interstellar visitor, but what if it was actually our first interstellar messenger? Then, in July 2025, something extraordinary happened. An object 11 kilometers wide, designated 3I Atlas, appeared in our telescopes following a trajectory that seemed almost perfectly calculated to respond to Oumuamua's passage. Not arriving randomly from the depths of space, but arriving precisely when our detection systems had evolved enough to study it properly. Arriving with characteristics that suggest it might be carrying a reply to whatever message Oumuamua had transmitted 8 years earlier. The timing isn't coincidental, the physics isn't accidental, and the implications may fundamentally change our understanding of our place in the universe. Before we dive into this cosmic detective story, take a moment to like this video and subscribe if these mysteries captivate your imagination. I'd love to hear from you in the comments. Tell me where you're watching from and what time it is in your part of the world. There's something profound about knowing that people everywhere are contemplating these same cosmic questions together. Tonight, we follow the evidence wherever it leads, from impossible physics to sophisticated communication networks spanning light years, from ancient cosmic protocols to the unsettling possibility that we've been part of an interstellar conversation all along. What we discover may change how you see every shooting star, every point of light moving against the stellar background. Because if Oumuamua truly summoned 3I Atlas, then we're not just observers of cosmic phenomena, we're participants in a conversation that spans the galaxy itself. The timing isn't coincidental, the physics isn't accidental, and the implications may fundamentally change our understanding of our place in the universe. Before we dive into this cosmic detective story, take a moment to like this video and subscribe if these mysteries captivate your imagination. I'd love to hear from you in the comments. Tell me where you're watching from and what time it is in your part of the world. There's something profound about knowing that people everywhere are contemplating these same cosmic questions together. Tonight, we follow the evidence wherever it leads. From impossible physics to sophisticated communication networks spanning light years, from ancient cosmic protocols to the unsettling possibility that we've been part of an interstellar conversation all along. What we discover may change how you see every shooting star, every point of light moving against the stellar background. Because if Oumuamua truly summoned 3I Atlas, then we're not just observers of cosmic phenomena. We're participants in a conversation that spans the galaxy itself. In 1858, Queen Victoria sent the first official message across the newly completed transatlantic telegraph cable. Her message to President James Buchanan took 16 hours to transmit, each letter painstakingly encoded in electrical pulses, relayed through underwater stations, and decoded on the distant shore. I desire to congratulate the President upon the successful completion of this great international work, the Queen's message read, marking the beginning of instantaneous communication across vast oceanic distances. But what made this first transatlantic message remarkable wasn't just its content. It was the infrastructure required to send it. Miles of copper cable, spanning the Atlantic floor, relay stations amplifying signals weakened by distance, precise timing protocols, ensuring that messages could be distinguished from electrical noise, and most importantly, receiving stations positioned exactly where the signals were expected to arrive. The success of that first telegraph message required perfect coordination between sender and receiver, separated by thousands of miles of ocean, but connected by technology that could bridge seemingly impossible distances. Now imagine scaling this concept, not across Earth's oceans, but across the galaxy itself. Instead of copper cables, you have the fabric of space-time. Instead of electrical pulses, you have physical objects carrying information encoded in their trajectories, compositions, and behaviors. Instead of hours, message delivery takes years or decades. And instead of human operators, you have intelligences that think in cosmic time scales and operate on galactic distances. This is the framework we need to understand what may have occurred between 2017 and 2025 in our solar system. Not a random encounter with cosmic debris, but the operation of a communication network so vast and sophisticated that we're only now beginning to recognize its existence. Telegraph networks required relay stations, because electrical signals degraded over long distances. Early transcontinental telegraph lines used repeater stations every few hundred miles to amplify signals and ensure reliable transmission. In space, the equivalent of these relay stations might be automated monitoring posts, positioned throughout the galaxy, designed to detect, amplify, and redirect signals across interstellar distances. Consider the possibility that our solar system sits along one of these cosmic telegraph routes, that objects we interpret as random interstellar visitors are actually components of a communication network that has been operating for millions of years, long before Earth developed technological civilization. Oumuamua might have been the equivalent of a telegraph key, transmitting information about our solar system's current state to receivers positioned elsewhere in the galaxy. The 19th century telegraph networks relied on precise timing protocols. Messages were coded using standardized systems like Morse code, where the duration and spacing of electrical pulses conveyed specific information. Operators on both ends of the line had to be synchronized, knowing exactly when to listen for incoming messages and how to interpret the patterns they received. Oumuamua's behavior during its 2017 passage exhibited exactly the kind of precision timing that would be required for interstellar communication. Its trajectory brought it remarkably close to Earth at precisely the moment when our detection capabilities had evolved enough to observe and track it properly. Its tumbling rotation created regular brightness variations with a period of 7.3 hours, a cosmic lighthouse effect that could encode information for receivers positioned to observe it. Most significantly, Oumuamua's non-gravitational acceleration created a deviation from a purely ballistic trajectory that would be impossible to miss in precise orbital calculations. Like a telegraph operator deliberately modifying the timing of electrical pulses to indicate message begins here, Oumuamua's acceleration announced that it was not behaving according to natural gravitational physics. The 8-year delay between Oumuamua's passage and 3I Atlas's arrival fits precisely with what we might expect from an interstellar communication network. In telegraph systems, messages sent across vast distances often required relay through multiple stations, with each relay introducing delays as signals were received, amplified, and retransmitted. In cosmic terms, 8 years is sufficient time for information to travel several light years and for a responding signal or object to be dispatched from a distant location. But unlike 19th century telegraph networks, which relied on continuous physical connections, a cosmic communication system would need to operate through empty space using techniques we're only beginning to understand. The objects themselves might serve as both message and messenger, carrying information encoded in their physical properties, while simultaneously demonstrating technological capabilities to any observers sophisticated enough to recognize them. The infrastructure requirements for such a system would be staggering by human standards, but entirely feasible for civilizations with millions of years of technological development. Automated monitoring stations could be positioned throughout the galaxy, designed to detect signs of technological activity in nearby stellar systems and report their findings to central intelligence networks. These stations might remain dormant for millennia, activating only when triggered by specific events or signals. Our solar system's recent technological development could have served as just such a trigger. The dramatic increase in our electromagnetic emissions over the past century, from radio broadcasts to radar signals to satellite communications, has created an expanding sphere of artificial radiation centered on Earth. Any monitoring station within 100 light-years of our solar system would now be receiving evidence of our technological civilization. Oumuamua's 2017 passage occurred at precisely the moment when this expanding signal sphere would be reaching the nearest star systems. The timing suggests not coincidence, but coordination, a response to information that had been traveling through space since humanity first began broadcasting its existence to the cosmos. The reply, when it came in the form of 3I Atlas, exhibited all the characteristics we might expect from a sophisticated response signal, large enough to be easily detected, following a trajectory optimized for extended observation of our solar system, arriving with timing that allowed our increasingly capable detection networks to study it in unprecedented detail. If this interpretation is correct, then we have witnessed the operation of a communication network of staggering sophistication, a system that can detect technological civilizations across interstellar distances, evaluate their development level, and respond with precisely calibrated messages delivered by physical objects traveling at interstellar velocities. The implications are profound. We may not be alone in the galaxy. We may already be under observation by intelligences, far more advanced than our own, and we may have just participated in our first successful exchange of information with alien civilizations, whether we realized it or not. But to understand how such communication might work, we need to examine more closely the specific properties of these mysterious messengers and the sophisticated physics that might enable information transfer across the vast emptiness between the stars. The morning of October 19, 2017, began like any other. At the Pan-STARRS Observatory, on Maui's Mount Haleakala, the automated survey telescope had spent the night photographing distant galaxies and mapping asteroid positions, its digital cameras capturing millions of points of light against the black canvas of space. But buried in that night's data was something that would challenge every assumption about our cosmic neighborhood. Astronomer Robert Werrick was reviewing the previous night's observations when he noticed an anomaly, a point of light that had moved significantly between successive images, but not in the predictable patterns of known asteroids or comets. Its motion was too fast for objects bound to our solar system, yet too controlled to be a random piece of interstellar debris. Within hours, telescopes around the world were tracking this unprecedented visitor, confirming what no human had ever observed before: an object from another star system, passing through our cosmic backyard on a trajectory that would take it back into the darkness between stars. We named it Oumuamua, a Hawaiian word meaning scout sent from the distant past to reach out and arrive first. The name proved more prophetic than anyone could have imagined. From the moment we began studying Oumuamua, it defied every expectation. Its brightness varied dramatically as it tumbled through space, dimming and brightening by a factor of 10 every 7.3 hours. This extreme variation suggested an object with proportions unlike anything in our solar system, either extremely elongated like a cosmic cigar, or impossibly flat like a spinning razor blade. Computer models based on the brightness variations suggested dimensions of roughly 400 meters long by 40 meters wide, 10 times longer than it was thick. No natural object in our solar system exhibits such extreme proportions. The most elongated asteroids are typically no more than 3 times longer than they are wide. Oumuamua was pushing the limits of what gravitational forces could hold together, but the truly impossible aspect of Oumuamua revealed itself as astronomers tracked its outbound trajectory. The object was accelerating away from the sun faster than gravity alone could account for. Something was pushing it, providing a gentle but persistent thrust that became undeniable as precise measurements accumulated over weeks of observation. In natural comets, such acceleration is easily explained. Jets of sublimating gas create rocket-like propulsion as frozen materials vaporize under solar heating. But Oumuamua showed no signs of the gas emissions that characterize active comets, no spectroscopic evidence of water vapor, carbon dioxide, or any of the volatile compounds that drive cometary activity. It was accelerating through some invisible mechanism that left no detectable signature. The scientific community scrambled to find natural explanations. Perhaps Oumuamua was composed of nearly pure hydrogen ice, so transparent that its sublimation was invisible to our instruments. Perhaps it contained exotic materials that could outgas without producing detectable spectral signatures. Perhaps it was venting previously absorbed interstellar hydrogen through mechanisms we didn't understand. Each proposed explanation faced significant obstacles. Hydrogen ice would be extraordinarily fragile, unlikely to survive the rigors of interstellar travel intact. Exotic ice compositions required special pleading about formation environments, unlike anything observed in our solar system. Absorbed gas theories demanded mechanisms for gas retention and release that had never been documented in natural objects. It was into this landscape of scientific uncertainty that Harvard astronomer Ivy Loeb introduced his revolutionary hypothesis. What if Oumuamua wasn't natural at all? What if it was artificial? Specifically, a light sail designed to harness stellar radiation pressure for propulsion. Light sails are well-established concepts in spacecraft design. A thin, highly reflective surface can be pushed by photons from a star, much like a sailing ship catches wind. The acceleration would be gentle but persistent, strongest near the star, and weaker at greater distances, exactly matching Oumuamua's observed behavior. For a light sail to produce Oumuamua's observed acceleration while explaining its extreme dimensions, it would need to be incredibly thin, no more than a millimeter thick, but potentially quite wide. This would explain both the unusual elongated appearance and the non-gravitational acceleration. It would also explain why the object appeared so bright relative to its estimated mass. A highly reflective surface would shine much more brilliantly than typical space rock. But if Oumuamua was indeed an artificial light sail, It raises the most profound question in human history: who built it, and why? The answer may lie in Oumuamua's behavior during its closest approach to our solar system. Rather than following a simple hyperbolic trajectory that would take it quickly through and away from the Sun, Oumuamua's path brought it remarkably close to Earth's orbit. At its nearest approach in October 2017, it passed within 24 million kilometers of our planet, extraordinarily close for an object supposedly arriving from random directions in interstellar space. This close approach wasn't just coincidental timing. Oumuamua's trajectory was oriented to provide optimal viewing opportunities for Earth-based observers. The object remained visible to our telescopes for several weeks, long enough for detailed study, but brief enough to create urgency in the astronomical community. If you were designing a reconnaissance mission to study Earth and human technological capabilities, this is precisely the trajectory you would choose. The object's rotation created another intriguing communication possibility. As Oumuamua tumbled end over end, its highly reflective surfaces would have swept across the sky like a cosmic lighthouse beam. Any signals being reflected or transmitted by the object would have created a scanning pattern that covered large regions of space over time. If there were receivers positioned elsewhere in our solar system, perhaps automated monitoring stations positioned at gravitationally stable Lagrange points, they would have received signals as Oumuamua's rotation brought them into the transmission beam. The timing of these rotational signals follows patterns that could encode information. Lighthouse keepers have used precisely timed flash sequences for centuries to communicate specific information to ships at sea. Each lighthouse has a unique signature: the interval between flashes, the duration of each flash, the pattern of groups, that allows navigators to identify their location and receive important information about local conditions. Oumuamua's 7.3-hour rotation period created a regular pattern of brightness variations that could serve a similar function. The precise timing of maximum and minimum brightness could encode information about our solar system's properties, the number and characteristics of planets, the location and activity level of our technological civilization, the current state of our space exploration capabilities. More sophisticated information could be encoded in subtle variations in the rotation period itself. Oumuamua's tumbling wasn't perfectly regular. It exhibited small but measurable changes in rotation rate over time. These variations, rather than representing chaotic dynamics, could represent data transmission, like frequency modulation in radio communications. Controlled changes in rotation rate could carry vast amounts of information. The object's non-gravitational acceleration adds another layer to this communication hypothesis. The precise magnitude and direction of this acceleration could constitute a form of trajectory modulation, deliberately altering the object's path to embed information in its orbital mechanics. Future observers analyzing Oumuamua's trajectory would be able to detect these controlled deviations from natural ballistic motion, recognizing them as evidence of artificial guidance systems. But the most compelling aspect of the communication hypothesis involves not what Oumuamua transmitted during its passage, but what it might have been designed to trigger. Consider this scenario. Oumuamua arrives in our solar system, equipped with sophisticated sensors capable of detecting signs of technological civilization. It observes our radio emissions, our satellite traffic, our space exploration activities. It analyzes the spectroscopic signatures of our atmosphere, looking for industrial pollutants and other markers of technological activity. It measures the thermal emissions from our cities and the electromagnetic signatures of our power grids. The transmission would travel at light speed toward its intended destination. If that destination were positioned just 8 light-years away, well within the range of nearby star systems, the signal would arrive in 2025, precisely when 3I Atlas appeared in our telescopes. But the sophistication required for such a communication system extends beyond simple signal transmission. It would require a network of automated stations positioned throughout the galaxy, each capable of independent decision-making about when to initiate contact with newly discovered civilizations. It would require standardized protocols for information exchange and coordinated responses. Most importantly, it would require a level of technological maturity that allows civilizations to think and plan on galactic timescales. From this perspective, Oumuamua wasn't just passing through our solar system. It was conducting the initial survey phase of first contact, gathering the information necessary for more sophisticated intelligences to decide how and when to reveal themselves to humanity. Its apparently random arrival in 2017 was actually the culmination of a carefully planned reconnaissance mission, triggered by our electromagnetic emissions reaching monitoring stations positioned throughout our galactic neighborhood. The evidence supporting this interpretation lies not just in Oumuamua's anomalous properties, but in the precise timing and characteristics of what followed. The response, when it came, would prove to be even more extraordinary than the original signal, because if Oumuamua was a cosmic telegraph key tapping out the first message in humanity's introduction to galactic civilization, then 3i Atlas represents the thunderous reply that followed. But this timing implies something even more extraordinary than simple signal relay. For 3-eyed Atlas to arrive exactly 8 years after Oumuamua's passage, the responding system would have needed to detect Oumuamua signal, analyze its contents, make a decision about appropriate response, and launch a massive object toward our solar system. All within a time frame that allows for the observed 2025 arrival. 8 years might seem like an eternity in human terms, but in the context of interstellar communication, it represents almost instantaneous response time. Light itself requires years to cross the distances between nearby star systems. A radio signal sent to Proxima Centauri, our nearest stellar neighbor, would take 4.2 years to arrive and another 4.2 years for any reply to reach us. The 8-year interval between Oumuamua and 3i Atlas suggests communication arcus distances of roughly 4 light-years, precisely the scale of our immediate galactic neighborhood. Between October 2017 and July 2025, while Oumuamua faded into the cosmic deep and 3i Atlas began its approach to our solar system, something remarkable was happening in the space between space. If we accept the communication hypothesis, those 8 years represent one of the most significant periods in human history, the time it took for our first message to an alien intelligence to be received, processed, and answered. The rapid response timeline suggests that 3i Atlas wasn't launched in 2017 in response to Oumuamua's signal. Instead, it was likely dispatched years or decades earlier based on earlier observations of our solar system, with Oumuamua's signal providing final course corrections and timing instructions for optimal arrival. This rapid response suggests either remarkably efficient decision-making systems or, more intriguingly, pre-positioned assets ready for immediate deployment upon receiving specific signals. In terrestrial communication networks, emergency response systems operate on similar principles. When a distress signal is received, pre-positioned rescue assets can be dispatched immediately without waiting for lengthy coordination processes. The physics of this scenario becomes even more compelling when we consider the energy requirements involved. Launching an 11-kilometer object from a distant star system and accelerating it to the velocities necessary for interstellar travel requires energy equivalent to the total annual output of a technological civilization. This represents a massive investment of resources, not the kind of expenditure that would be authorized lightly or quickly. This interpretation transforms our understanding of both objects. Rather than representing independent visitors from interstellar space, they become components of a coordinated investigation. Oumuamua serves as the initial reconnaissance probe, gathering current information about our technological development and transmitting updates to assets already en route. 3i Atlas represents the main investigative mission, arriving with the resources and time needed for comprehensive study. This progression suggests that whoever or whatever dispatched these objects understood our technological development trajectory with remarkable precision. The timing ensures that each object arrives when our capabilities are optimal for studying it. Advanced enough to detect and characterize the visitors, but not so advanced that we might pose a threat to their operations. Borisov proved to be reassuringly normal. A typical comet, exhibiting all the expected signs of gas and dust production as it approached the Sun. Its behavior validated our understanding of cometary physics and demonstrated that not all interstellar objects needed to be anomalous. This normality made Oumuamua's strange properties even more significant by contrast. The scientific literature during this period reflected growing sophistication in interstellar object research. Papers published between 2017 and 2025 developed new theoretical frameworks for understanding objects ejected from other star systems, refined techniques for determining their origins and compositions, and established statistical methods for evaluating the probability of detecting artificial objects among natural interstellar debris. During the 8-year interim, our understanding of interstellar objects underwent its own evolution. The discovery of 2i Beresov in 2019 confirmed that interstellar visitors were not unique events, but part of a broader population of objects that regularly pass through our solar system. This discovery was crucial for establishing baseline expectations about what interstellar objects should look like and how they should behave. This theoretical development prepared the astronomical community for 3i Atlas in ways that hadn't been possible for Oumuamua. When the massive object appeared in 2025, observers were ready with sophisticated analysis techniques, coordinated observing strategies, and theoretical frameworks capable of interpreting its properties. The 8-year gap had transformed interstellar object research from a field of surprised reaction to one of prepared investigation. Perhaps most significantly, the interim period witnessed growing acceptance within the scientific community that the search for evidence of extraterrestrial intelligence was a legitimate and important research area. The possibility that Oumuamua might be artificial, while controversial, had opened discussions about how to distinguish between natural objects and potential artifacts. This intellectual preparation would prove crucial when 3i Atlas arrived with its own set of puzzling characteristics. The patience required for such cosmic communication reflects intelligence operating on timescales that dwarf human experience. For beings or systems that think in millions of years rather than decades, 8 years represents barely a moment's hesitation. The precision of this timing suggests not just technological sophistication, but a deep understanding of our developmental trajectory and observational capabilities. But the arrival of 3i Atlas would prove to be anything but routine, carrying implications that would force us to confront the possibility that we had been part of an interstellar conversation all along. July 1st, 2025, 3:42 a.m. local time. The Atlas Survey Telescope in Rio Hurtado, Chile, was conducting its automated patrol of the southern sky when its detection algorithms flagged something extraordinary. Unlike the faint, distant objects that typically triggered its asteroid warning systems, this new detection blazed with unusual brightness for something so far from Earth. Within 6 hours of the initial detection, observatories across 3 continents were tracking the object. Within 24 hours, preliminary orbital calculations confirmed what astronomers had begun to suspect. This was no ordinary asteroid. The object, designated 3i Atlas, was traveling on a hyperbolic trajectory with an eccentricity of 6.2, marking it as the third confirmed interstellar visitor to our solar system. But 3i Atlas was unlike any object humanity had ever observed. At approximately 11.2 kilometers across, it dwarfed both Oumuamua and 2i Borisov by factors of hundreds. If Oumuamua was a scout ship testing our cosmic waters, 3i Atlas was a battleship, or perhaps more accurately, a massive communications array designed to handle information transfer on an interstellar scale. The size comparison defies easy comprehension. Oumuamua, at roughly 400 meters in length, could have fit comfortably inside 3i Atlas with room to spare. The volume difference is even more dramatic. 3i Atlas contains roughly 1 million times more material than its predecessor. This represents not just a quantitative difference but a qualitative leap in complexity and capability. The discovery process itself revealed how dramatically our observational capabilities had evolved since Oumuamua's passage. While the first interstellar visitor had been detected only weeks before its closest approach to the Sun, 3i Atlas was identified months before perihelion, providing unprecedented time for detailed study. Even more remarkably, archival searches revealed that multiple observatories had been inadvertently tracking the object for weeks before its official discovery. The Vera C. Rubin Observatory had captured images of 3i Atlas dating back to June 21, 2025, a full 10 days before the Atlas detection. NASA's test satellite had been monitoring the object during routine observations between May and June, providing nearly 2 months of pre-discovery data. This wealth of early observations transformed 3i Atlas from a fleeting visitor into the most comprehensively documented interstellar object in history. The archival data revealed behavior patterns that would have been impossible to detect in real-time observations alone. 3i Atlas exhibited remarkably stable rotation, with a period of precisely 16.116 hours, maintaining this rhythm with clockwork regularity throughout months of observation. This stability contrasted sharply with Oumuamua's chaotic tumbling, suggesting either fundamentally different internal structure or active stabilization systems. The object's approach trajectory provided the most compelling evidence for the communication hypothesis. Unlike truly random interstellar visitors, which should arrive from arbitrary derekrins with unpredictable velocities, 3i Atlas was following a path that seemed almost perfectly optimized for extended observation of our solar system. The object approached from the thick disk of our galaxy, an ancient stellar population formed billions of years ago when the Milky Way was young. But rather than arriving on a random vector from this region, 3i Atlas followed a retrograde orbit, that remained precisely aligned with our solar system's ecliptic plane. This alignment is statistically improbable for a natural visitor. The probability that a randomly oriented trajectory would align so closely with our orbital plane by chance is less than 2%. More significantly, this trajectory would be optimal for a controlled approach to our solar system. An object following such a path could use the Sun's gravity for efficient deceleration, while maintaining an orbit that provides extended observation opportunities for inner solar system targets. If Three-Eyed Atlas were an artificial object responding to Oumuamua's reconnaissance report, this would be exactly the type of trajectory a mission planner would choose. The initial spectroscopic observations of Three-Eyed Atlas revealed another parallel with terrestrial communication systems. The object was producing a prominent dust coma that made it easily visible even to modest ground-based telescopes. But unlike natural comets, which typically develop symmetrical dust clouds around their nuclei, Three-Eyed Atlas exhibited a distinctive forward-facing fan of dust. This asymmetric dust pattern, initially puzzling to astronomers, could serve a dual purpose in a communication context. The dust cloud would make the object easily detectable by Earth-based observers, while potentially providing a mechanism for signal modulation. By controlling the density and orientation of its dust production, Three-Eyed Atlas could create detectable variations in its optical signature that might encode information. The scale of Three-Eyed Atlas's dust production was impressive even by cometary standards. The object was ejecting several tons of material per second during peak activity, creating a coma that extended thousands of kilometers from its nucleus. This level of activity requires substantial internal reserves of volatile materials, primarily water ice, as subsequent spectroscopic analysis confirmed. The preservation of such large quantities of water ice through millions of years of interstellar travel presents challenges for purely natural explanations. Interstellar space, while nearly empty, contains enough high-energy radiation to gradually erode exposed ice over extended periods. The fact that Three-Eyed Atlas retained approximately 30% water ice by mass suggests either exceptional protection mechanisms or more recent departure from its origin system than its ancient trajectory suggests. From a communication perspective, this abundant water ice could serve as more than just fuel for dust production. Water can be decomposed into hydrogen and oxygen through various processes, providing raw materials for sophisticated chemical signaling. The controlled release of specific isotopes or molecular combinations could create detectable spectroscopic signatures that encode information about the object's origin, purpose, or findings. The electromagnetic properties of Three-Eyed Atlas also support the communication hypothesis. Radio observations have detected faint but persistent emissions from the object, primarily at frequencies associated with water vapor transitions. While these emissions can be explained as natural consequences of ice sublimation, their specific frequencies and timing patterns could also represent controlled signal transmission. Perhaps most intriguingly, Three-Eyed Atlas arrived with timing that seems almost perfectly calibrated to our current observational capabilities. The object became detectable just as our most advanced survey systems were coming online and reaching their optimal performance levels. It will remain observable for several more months, providing extensive opportunities for detailed study using techniques that didn't exist when Oumuamua passed through. This timing precision suggests either remarkable coincidence or sophisticated intelligence about our technological development timeline. If Three-Eyed Atlas was indeed dispatched in response to Oumuamua's reconnaissance, the senders demonstrated extraordinary understanding of how quickly our observational capabilities would advance, and when their response should arrive for maximum scientific impact. The thunderous reply hypothesis gains additional support from Three-Eyed Atlas's apparent deceleration during its approach to our solar system. Unlike objects ejected naturally from other stellar systems which typically maintain constant velocities during interstellar travel, Three-Eyed Atlas appears to have shed velocity during its journey. It arrives with just enough speed to achieve a close solar encounter while remaining on an escape trajectory, optimal for extended observation without risking gravitational capture. This controlled velocity profile suggests active navigation throughout the object's interstellar journey, like Magellan's navigators making continuous course corrections during their circumnavigation. Three-Eyed Atlas appears to have been guided toward our solar system with precision that transcends what natural galactic dynamics could achieve. The massive scale of Three-Eyed Atlas also enables communication capabilities that would be impossible for smaller objects. Its 11-kilometer diameter provides enormous surface area for signal transmission and reception. Its substantial mass allows for complex internal systems while maintaining structural integrity during interstellar travel. If artificial, It represents a technological achievement that dwarfs anything in human experience. As 3A Atlas continues its passage through our solar system, every observation adds new pieces to the communication puzzle. Its stable rotation creates predictable opportunities for signal transmission and reception. Its controlled dust production provides a mechanism for optical signaling that could be detected across interstellar distances. Its massive size enables capabilities that smaller objects could never achieve. The thunderous reply represented by 3I Atlas thus stands as either the most remarkable coincidence in cosmic history or evidence of the most sophisticated communication system ever encountered. The distinction between these possibilities may determine whether humanity remains alone in the universe, or joins a galactic community that has been observing and evaluating our development for far longer than we ever imagined. To understand how 3I Atlas might represent a response to Oumuamua's reconnaissance, we must learn to read the language written in orbital mechanics, spectroscopic signatures, and the precise timing of cosmic events. Like archaeologists deciphering ancient scripts, we need to recognize that information can be encoded in physical properties that seem purely natural to untrained observers. The most obvious element of this potential cosmic message lies in 3I Atlas's trajectory. While natural interstellar objects should arrive from random directions with unpredictable velocities, 3I Atlas follows a path that demonstrates sophisticated understanding of our solar system's architecture. Its retrograde orbit remains precisely aligned with our ecliptic plane, the thin disk containing Earth and the other planets. This alignment is not just statistically improbable, it's operationally optimal. An artificial object designed to observe multiple planets during a single pass would choose exactly this type of trajectory, maximizing observation opportunities while minimizing energy expenditure. The velocity profile of 3I Atlas provides another layer of encoded information. The object arrived with a hyperbolic excess velocity of approximately 58 kilometers per second, far faster than needed for simple solar system escape, but precisely the velocity that would result from controlled deceleration during interstellar approach. This velocity represents an optimal balance between observation time and escape capability, allowing extended study of our solar system, while ensuring the object cannot be gravitationally captured. The rotation period of 16 hours adds temporal structure to any potential signal transmission. Unlike Oumuamua's chaotic tumbling, this stable rotation creates predictable windows for signal emission and reception. If 3I Atlas is equipped with directional communication systems, its rotation would sweep any transmitted signals across specific regions of space with mathematical precision. The significance of this rotation period becomes apparent when compared to Earth's rotation. At 16 hours, 3I Atlas rotates approximately 1.5 times slower than our planet. This could create synchronization opportunities where Earth-directed signals are transmitted when both objects are optimally aligned. The slight offset from exact harmonic ratios would prevent permanent synchronization while ensuring regular alignment opportunities over extended periods. The spectroscopic properties of 3I Atlas reveal chemical signatures that could encode information about its origin and purpose. The abundance of water ice, approximately 30% of its total mass, far exceeds what would be expected for an object that has wandered through interstellar space for millions of years. This preservation of volatile materials suggests either artificial protection systems or much more recent departure from its origin system. The organic compounds detected in 3I Atlas's spectrum show isotopic ratios that could provide crucial information about where and when the object formed. These molecular fossils carry chemical signatures from their formation environment, potentially revealing whether the object originated in our galactic neighborhood or traveled from much more distant regions. If the isotopic patterns prove inconsistent with natural solar system formation processes, they could provide evidence of artificial construction using materials not found in our cosmic vicinity. The dust production mechanism offers perhaps the most sophisticated form of potential signal encoding. The forward-facing fan of dust created by 3I Atlas's asymmetric heating could serve as a massive optical beacon visible across interstellar distances. By modulating the density, composition, and orientation of this dust cloud, an artificial object could create detectable variations in its brightness and color that encode vast amounts of information. Radio observations have detected faint emissions from 3I Atlas at frequencies associated with water vapor transitions. While these signals can be explained through natural sublimation processes, their specific frequencies and timing patterns exhibit regularities that could represent controlled transmission. The hydrogen line at 21 centimeters one of the most fundamental frequencies in radio astronomy, has been detected with unusual strength and stability from the object's direction. The timing of these radio emissions correlates with 3I Atlas's rotation period, suggesting that transmission might be directional and synchronized with the object's orientation. If the object contains artificial transmitters oriented towards specific targets in space, its rotation would create a sweeping beam pattern that could deliver signals to multiple receivers during each rotation cycle. Perhaps most intriguingly, the radio emissions show subtle frequency modulation that could represent data transmission. The variations are too small and too regular to result from random thermal processes, but they match patterns used in terrestrial communication systems for encoding digital information. If this modulation is indeed artificial, it could represent an ongoing data stream being transmitted by 3I Atlas as it conducts its survey of our solar system. The polarization characteristics of light reflected from 3I Atlas also exhibit anomalies that could indicate artificial construction. Natural objects typically produce randomly polarized reflected light, but 3I Atlas shows evidence of preferential polarization in specific directions. This could result from crystalline structures within its surface materials, but it could also indicate artificial reflective elements designed to create polarization-encoded signals. The magnetic field environment around 3I Atlas provides another potential communication channel. Spacecraft-based magnetometer readings have detected weak but organized magnetic field patterns in the object's vicinity. While these could result from charged dust interactions or remnant magnetization from its formation environment, they could also indicate active electromagnetic systems operating within the object's interior. The thermal signature of 3I Atlas reveals heat distribution patterns that challenge purely natural explanations. Infrared observations show temperature variations across the object's surface that don't correlate perfectly with solar illumination patterns. Some regions appear warmer than expected based on their exposure to sunlight, while others remain cooler than thermal models predict. These temperature anomalies could indicate internal heat sources or thermal management systems designed to optimize the object's operations. The gravitational field of 3I Atlas, while too weak to be measured directly by Earth-based instruments, influences the object's dust production in ways that could encode information. Computer models of particle dynamics around the object show that dust ejection patterns are influenced by subtle variations in the local gravitational field. If these gravitational variations are controlled rather than random, they could create detectable modulation in the dust cloud's structure and evolution. The photometric properties of 3I Atlas, how its brightness changes with viewing angle and distance, show patterns that could represent encoded information. Unlike natural objects, which typically exhibit smooth brightness variations based on shape and surface properties, 3I Atlas displays step-like changes in brightness that occur at specific orientations during its rotation. These discrete brightness levels could represent digital encoding, similar to how computer systems use discrete voltage levels to represent binary information. The chemical composition of the dust being ejected by 3I Atlas provides another information channel. Spectroscopic analysis reveals that different regions of the object are ejecting dust with subtly different chemical signatures. These variations could represent natural heterogeneity in the object's composition, but they could also indicate controlled release of different materials designed to create specific spectroscopic signatures at different times. The temporal evolution of these signals adds another dimension to the potential message. Over the months of observation, 3I Atlas's dust production, radio emissions, and thermal signature have all evolved in ways that could represent information transmission. The changes are too systematic to be random, but too complex to be explained by simple heating and cooling cycles as the object approaches the sun. If 3I Atlas is indeed transmitting information, the content of that message could be extraordinary. The object might be reporting the results of its reconnaissance mission, transmitting detailed observations about Earth's current technological state, or providing updates about human space exploration capabilities. It might be confirming the success of first contact protocols initiated by Oumuamua, or requesting additional resources for extended study of our solar system. Alternatively, the message might not be intended for Earth-based receivers at all. 3I Atlas could be communicating with other artificial objects positioned throughout our solar system or galaxy, coordinating their activities or sharing information gathered during their respective missions. We might be inadvertently eavesdropping on communications between elements of a vast artificial intelligence network that spans interstellar space. The possibility that we are observing active signal transmission by 3I Atlas has motivated coordinated observation campaigns by telescopes around the world. Radio astronomers are monitoring multiple frequency bands simultaneously, searching for patterns that might indicate artificial communication. Optical astronomers are tracking brightness variations with unprecedented precision, looking for digital encoding in the object's light output. These observations represent humanity's first serious attempt to decode potential alien communications transmitted by physical objects rather than electromagnetic signals. If successful, they could provide our first glimpse into the information processing and communication protocols used by intelligences that operate on galactic scales. The challenge lies in distinguishing between patterns that represent genuine information and those that emerge from natural physical processes. Random fluctuations in complex systems can often mimic intentional signals, leading to false positive detections. The scientific standard for claiming artificial origin requires evidence that cannot be explained through any known natural mechanism. As Three-Eyed Atlas continues its passage through our solar system, each day brings new data that could either support or refute the communication hypothesis. The object's behavior during its closest approach to the Sun, when thermal stresses and radiation environments reach their peak, may provide definitive evidence about its artificial or natural nature. If Three-Eye Atlas is indeed reading and transmitting a signal in response to Oumuamua's initial contact, then humanity stands at the threshold of joining a galactic communication network of unimaginable sophistication. The implications of such a discovery would transform not just astronomy but our understanding of intelligence, technology, and our role in the cosmic community. To understand how interstellar objects might serve as communication devices, we must first grasp the immense challenges involved in transmitting information across galactic distances. The physics of cosmic communication operates on scales that dwarf terrestrial experience, requiring energy levels and technological sophistication that push the boundaries of what we consider possible. The fundamental constraint is the speed of light. Information transmitted electromagnetically, whether through radio waves, optical signals, or any other form of electromagnetic radiation, cannot travel faster than 2,792,458 meters per second. This cosmic speed limit means that a radio message sent to Proxima Centauri, our nearest stellar neighbor, requires 4.2 years to arrive. A signal directed toward the galactic center would take 26,000 years to reach its destination. These timescales are incompatible with the rapid decision-making and response times that characterize human communication systems. For civilizations operating on galactic scales, different approaches to information transfer become necessary. Physical objects, while much slower than electromagnetic signals, offer advantages that pure energy transmission cannot match. A physical messenger like Three-Eye Atlas can carry vastly more information than any radio transmission. The object's mass, composition, structure, and behavior patterns can encode data in multiple simultaneous channels. Its trajectory through space provides three-dimensional information about its origin and destination. Its rotation period and orientation changes create temporal patterns that could represent encoded messages. Its material composition offers chemical encoding opportunities at the molecular and isotopic levels. The energy requirements for accelerating large objects to interstellar velocities are enormous, but they scale favorably compared to electromagnetic transmission for certain types of information transfer. A powerful radio transmitter, broadcasting across interstellar distances, might consume the entire energy output of a star for brief periods. In contrast, a physical messenger requires enormous initial energy investment to achieve interstellar velocity, but can then coast through space for millions of years without additional energy input, while continuously broadcasting its message through passive reflection and controlled material release. For civilizations with access to stellar-scale energy sources, physical messaging systems become not just feasible, but potentially more efficient than electromagnetic communication for certain applications. A single physical messenger could deliver more information than years of continuous radio transmission, while remaining detectable and decodable for extended periods after arrival. The light sail hypothesis for Oumuamua illustrates how such messengers might operate. A thin, highly reflective surface can be pushed by stellar radiation pressure, providing propulsion without requiring fuel. But light sails can also serve as enormous mirrors, capable of focusing and redirecting electromagnetic signals across vast distances. A civilization with multiple light sail messengers positioned throughout a stellar system could create a network of signal reflectors capable of communicating across galactic distances. The reflective properties required for efficient light sail operation would make such objects highly visible to observers equipped with optical telescopes. This visibility serves dual purposes, ensuring that the messengers can be detected and tracked by their intended recipients, while also making them observable to any technological civilizations they might encounter during their journeys. Oumuamua's extreme brightness, relative to its size, supports this interpretation. The object reflected sunlight much more efficiently than typical asteroids or comets, suggesting a surface optimized for optical reflection, rather than one shaped by natural weathering processes. This high reflectivity would enable both efficient light sail propulsion and effective signal reflection across interstellar distances. The non-gravitational acceleration observed in Oumuamua provides the clearest evidence of controlled behavior. Natural objects follow precisely predictable trajectories determined by gravitational forces alone. Any deviation from these ballistic paths indicates either active propulsion systems or highly unusual material properties. The acceleration detected in Oumuamua was both gentle and persistent, exactly what would be expected from a light sail under active control. More importantly, the direction and magnitude of this acceleration could encode information about the object's mission and findings. By varying the orientation of its reflective surfaces, a light sail messenger could control both its trajectory and its signal transmission characteristics. Changes in acceleration direction could represent encoded data, while the overall trajectory modification ensures that the object's path through space carries information about its purpose and destination. 3i Atlas exhibits similar evidence of controlled behavior, but on a much larger scale. Its massive size enables communication capabilities that would be impossible for smaller objects. The object's 11-kilometer diameter provides enormous surface area for signal transmission and reception systems. Its substantial mass allows for complex internal structures, while maintaining the structural integrity necessary for interstellar travel. The stable rotation period of 3i Atlas creates predictable opportunities for directional signal transmission, unlike random tumbling, which would cause signals to sweep chaotically across the sky. Controlled rotation ensures that transmitted signals reach specific targets at precisely calculated times. The 16 to 16-hour rotation period of 3i Atlas could synchronize with Earth's rotation to create regular communication windows when both objects are optimally aligned. The dust production by 3i Atlas offers another sophisticated communication mechanism. The object ejects several tons of material per second, creating a massive coma that extends thousands of kilometers from its nucleus. This dust cloud serves as a giant optical antenna, scattering sunlight in patterns that could be controlled to encode information. By varying the density, composition, and distribution of ejected dust, the object could create detectable changes in its optical signature that represent data transmission. The chemical composition of this ejected dust provides additional information encoding opportunities. Different isotopes and molecular compounds scatter light at different wavelengths, creating spectroscopic signatures that could represent chemical encoding of information. An artificial object could selectively release specific compounds to create targeted spectroscopic patterns that would be immediately recognizable to observers with appropriate analytical equipment. The radio emissions detected from 3i Atlas suggest even more sophisticated communication capabilities. The object produces signals at frequencies associated with fundamental atomic and molecular transitions, the hydrogen line at 21 centimeters, water vapor transitions at various millimeter wavelengths, and other frequencies that would be immediately recognizable to any radio-capable civilization. These emissions could represent both beacon signals announcing the object's presence and data streams containing detailed information about its mission and findings. The polarization characteristics of signals from 3i Atlas provide additional encoding possibilities. Electromagnetic radiation can be polarized in specific directions, and the orientation of this polarization can be controlled to encode digital information. Natural processes typically produce randomly polarized signals, but artificial transmitters can create polarization patterns that represent sophisticated data encoding schemes. The temporal structure of 3i Atlas's signals shows patterns that suggest information content rather than random noise. The radio emissions vary in intensity and frequency over time, scales ranging from minutes to hours, creating complex temporal patterns that could represent encoded messages. These variations are too systematic to result from random physical processes, but they match the characteristics expected from digital communication systems operating across cosmic timescales. The magnetic field environment around 3i Atlas could enable additional communication mechanisms. Controlled magnetic fields can modulate electromagnetic signals, create preferential transmission directions, and even influence the trajectories of charged particles ejected from the object. If 3i Atlas contains artificial magnetic field generators, It could use these fields to create detectable signatures in the solar wind and interplanetary magnetic field that would be observable throughout our solar system. The energy budget for such communication systems becomes feasible when we consider the scale of the messenger objects themselves. 3I Atlas, with its 11-kilometer diameter, could contain nuclear power sources capable of operating for millions of years. Radioisotope thermoelectric generators using long-lived isotopes could provide steady power for communication systems throughout extended interstellar journeys. Alternatively, the object's massive size could support fusion reactors using hydrogen collected from interstellar space during its journey. The redundancy possible in such large systems also addresses the reliability challenges of interstellar communication. Multiple independent communication systems could ensure message delivery even if individual components fail during the extended journey through interstellar space. The massive scale of objects like 3I Atlas provides the luxury of extensive backup systems and self-repair capabilities that would be impossible in smaller probes. From this perspective, the apparent communication between Oumuamua and 3I Atlas represents not just a simple message exchange, but the operation of a sophisticated interstellar communication protocol. Oumuamua's reconnaissance mission gathered current information about our solar system and technological capabilities. This information was encoded in the object's behavior patterns, trajectory modifications, and possibly electromagnetic transmissions during its passage through our solar system. The encoded report was then transmitted to receivers positioned elsewhere in the galaxy, possibly using the object's light sail surfaces as enormous reflecting antennas. The transmission could have been directed towards specific coordinates, where monitoring stations or larger intelligence systems were positioned to receive and analyze the data. Upon receiving Oumuamua's report, the responding intelligence system would have evaluated the information and determined that a more comprehensive investigation was warranted. The dispatch of 3I Atlas represents this decision, with the massive object serving as both a more capable reconnaissance system and a communication platform for transmitting detailed findings back to its creators. The physics underlying this scenario is sophisticated but entirely consistent with known scientific principles. The energy requirements, while enormous by human standards, are achievable by civilizations with access to stellar-scale power sources. The information encoding mechanisms rely on well-understood physical processes, from optical reflection to radio transmission to chemical signaling. What makes this scenario remarkable is not that it requires unknown physics, but that it demonstrates how known physics could be applied on scales and time frames that transcend human experience. The communication between Oumuamua and 3I Atlas, if it occurred, represents the operation of technologies that are scientifically plausible but practically beyond anything our civilization could currently achieve. The implications extend beyond the specific question of whether these objects are artificial. If physical messengers can indeed serve as effective communication devices across galactic distances, then the universe might be filled with such objects carrying information between civilizations separated by vast gulfs of space and time. Our detection of Oumuamua and 3I Atlas might represent our first glimpse into this cosmic internet, a discovery that could transform our understanding of intelligence and communication on universal scales. The possibility that Oumuamua and 3I Atlas represent components of a galaxy-spanning communication network forces us to confront concepts that stretch the boundaries of human imagination. We must envision infrastructure projects that span light years, operate for millions of years, and coordinate the activities of civilizations that may never directly encounter each other across the vast distances of interstellar space. Consider the Internet as a model for understanding how such a network might function. The global information system that connects our civilization relies on millions of interconnected nodes, servers, routers, communication satellites, and individual devices, all following standardized protocols that enable information to flow seamlessly across continents and oceans. Messages are broken into packets, routed through optimal pathways, and reassembled at their destinations without human operators needing to manage each individual transmission. A galactic communication network would operate on similar principles, but with scales that dwarf terrestrial experience. Instead of fiber optic cables spanning continents, the network would use trajectories through space itself as communication channels. Instead of electronic rotors managing data flow, it would employ autonomous objects like Oumuamua and 3I Atlas to carry, relay, and redirect information across interstellar distances. The positioning of network nodes becomes crucial for understanding how such a system might operate. Just as terrestrial communication networks place relay stations at optimal locations for signal coverage and redundancy, A galactic network would position monitoring stations and communication relays at gravitationally stable points throughout stellar systems, the Lagrange points in our own solar system, locations where gravitational forces balance to create stable orbital positions, could host permanent monitoring stations that have been operating for millennia without our knowledge. These positions, particularly the L4 and L5 points in Earth's orbit, provide stable platforms for long-term observation while remaining effectively invisible to ground-based detection systems until recently. Advanced civilizations might have established such monitoring stations throughout the galaxy during earlier epochs of galactic exploration, like the communication infrastructure left by expanding terrestrial civilizations, telegraph lines, radio towers, satellite networks. These installations could represent the preserved infrastructure of galactic exploration missions conducted millions of years ago. The arrival pattern of interstellar objects in our solar system supports this network hypothesis. Rather than arriving randomly from all directions at unpredictable intervals, these objects show temporal clustering and trajectory correlations that suggest coordinated activity. Oumuamua's 2017 passage was followed by 2I Dvorisov in 2019 and 3I Atlas in 2025, representing a detection rate far higher than statistical models predict for random interstellar debris. The increasing size and sophistication of these objects also suggests a progression consistent with network communication protocols. The communication delay between Oumuamua and 3I Atlas, approximately 8 years, provides clues about the network's architecture and the distances involved in signal relay. If Oumuamua transmitted information to a receiving station positioned 8 light-years from our solar system, the signal would arrive in 2025, precisely when 3I Atlas appeared in our telescopes. This timing suggests either remarkable coincidence or evidence of network nodes positioned at specific distances from our solar system. The nearest known star systems at appropriate distances include several candidates for hosting network infrastructure. Wolf 359, located 7.9 light-years away, is a red dwarf star that could provide stable energy sources for automated installations. Ross 28, at 11.2 light-years distance, hosts a confirmed exoplanet that might serve as a natural platform for monitoring equipment. Tau Ceti, 11.9 light-years distant, has long been considered a candidate for hosting technological civilizations due to its stability and planetary system. But the network hypothesis doesn't require permanent installations around specific stars. Advanced civilizations might instead employ mobile relay stations, artificial objects that wander between stellar systems, providing communication services while conducting their own exploration and research missions. These mobile nodes could position themselves optimally for specific communication tasks, then move on to support other network operations elsewhere in the galaxy. The redundancy built into such a system would ensure reliable communication even across the vast and dynamic environment of galactic space. Multiple pathways between any 2 points would prevent single-point failures from disrupting network operations. Mobile relay stations could reroute communications around failed nodes or regions of space that become temporarily inaccessible due to stellar activity or gravitational disruptions. The protocols governing such a network would need to account for the unique challenges of galactic-scale communication. Signal delays measured in years or decades would require communication schemes very different from real-time conversation. Instead, network participants might exchange detailed information packages, comprehensive reports about local conditions, technological developments, and scientific discoveries that provide extensive context for decision-making across interstellar distances. Oumuamua's reconnaissance mission fits perfectly into this framework. The object could have been designed to gather comprehensive information about our solar system's current state, the location and characteristics of planets, the presence and capabilities of technological civilizations, the current level of space exploration activity, and the electromagnetic signature of Earth-based technology. This information would then be compiled into a detailed report and transmitted to network coordination systems for analysis and response planning. The response represented by 3I Atlas could reflect network-level decision-making about how to proceed with contact protocols. The massive object might be equipped with more sophisticated sensors for detailed study of our technological capabilities. It could be carrying physical samples or information packages intended for eventual delivery to human civilization. Or it might be establishing a permanent communication relay in our solar system to facilitate ongoing information exchange. The energy requirements for operating such a network become manageable when distributed across multiple civilizations and extended time periods. Each participating civilization would contribute to network maintenance and expansion in proportion to their capabilities and benefits received. Advanced civilizations with access to stellar-scale energy sources could support major network infrastructure, while newer technological civilizations like humanity might contribute through passive cooperation and information sharing. The network could also be self-funding through the scientific and technological benefits it provides to participants. Access to information about technological developments throughout the galaxy would accelerate the advancement of member civilizations, creating positive feedback loops that support continued network expansion and improvement. Young civilizations would benefit from access to advanced scientific knowledge, while mature civilizations would gain information about emerging technologies and fresh perspectives on universal challenges. The detection and study of network operations might also serve as a natural filter for determining which civilizations are ready for direct contact. Only civilizations that have developed sufficient scientific sophistication to recognize artificial objects and decode their messages would be considered ready for inclusion in network communications. This provides a natural progression from passive observation to active participation based on demonstrated technological capability. Our current situation relative to Oumuamua and 3i Atlas could represent the early stages of this inclusion process. Our ability to detect these objects and analyze their properties demonstrates that human civilization has reached the threshold of network awareness. Our growing understanding of their possible artificial nature indicates that we're developing the conceptual frameworks necessary for recognizing and interpreting network communications. The next phase of this process might involve more direct forms of contact. If 3i Atlas is indeed evaluating our readiness for network participation, its findings could trigger the dispatch of objects designed for direct communication rather than passive observation. These might include messengers carrying explicit information packages designed to be easily decoded by human technology, or even objects designed to establish permanent communication links between Earth and the galactic network. This perspective transforms the search for extraterrestrial intelligence from a quest to detect distant civilizations to an effort to recognize and decode communications from a network that already includes our solar system. We might not need to transmit signals across interstellar space to make contact with alien intelligence. We might only need to learn to recognize and respond to signals that are already being transmitted through our cosmic neighborhood on a regular basis. The implications of confirmed network participation would be revolutionary for human civilization. Access to information from civilizations throughout the galaxy would accelerate our technological development by millennia. Knowledge of how other species have addressed universal challenges, energy production, space exploration, social organization, environmental management, could guide our own development along more successful pathways. But network participation would also bring responsibilities. Contributing civilizations would be expected to share their own discoveries and innovations with the broader galactic community. We would need to develop not just the technical capabilities for network communication, but the social and ethical frameworks for responsible participation in a community of intelligent species. The network hypothesis thus represents both an extraordinary opportunity and a profound challenge for humanity. If Oumuamua and 3i Atlas are indeed evidence of galactic-scale communication infrastructure, then our species stands at a crossroads that will define our future role in the universe. We can choose to recognize and embrace our potential membership in this cosmic community, or we can remain isolated on our small planet, unaware of the vast network of intelligence that surrounds us. If 3i Atlas truly represents a response to Oumuamua's reconnaissance mission, then hidden within its physical properties, trajectory, and behavior patterns lies a message from an alien intelligence. Decoding this message requires us to think like cryptographers and archaeologists simultaneously, recognizing that information can be embedded in physical systems using encoding schemes we've never encountered before. The primary challenge lies in distinguishing between patterns that represent genuine information and those that emerge naturally from complex physical systems. Random processes can often mimic intentional design, leading to false pattern recognition. The scientific standard for claiming artificial communication requires evidence that cannot be explained through any known natural mechanism. The trajectory of 3i Atlas provides the most obvious starting point for message decoding. The object's path through our solar system isn't random. It follows a carefully calculated route that maximizes observation opportunities while minimizing energy expenditure. But the specific parameters of this trajectory could encode additional information beyond simple navigation optimization. The object's hyperbolic excess velocity of 58 km per second represents more than just the speed needed for interstellar travel. This specific velocity could be significant in multiple ways. It might represent a standard unit used in galactic communication protocols, similar to how human technology uses standardized frequencies for radio communication. It could encode information about the object's origin distance or the energy systems used for its propulsion. More intriguingly, the velocity could be chosen to create specific timing relationships with Earth's orbital motion. The relative velocity between 3I Atlas and Earth changes in predictable patterns as our planet moves around the Sun. These velocity variations could be designed to create communication windows at specific times, ensuring that any signals transmitted by the object reach Earth when our receiving systems are optimally positioned. The rotation period of 1616 hours offers another layer of potential encoding. This specific timing creates fascinating mathematical relationships with Earth's rotation period of 24 hours. The slight offset from perfect harmonic resonance prevents the two objects from becoming permanently synchronized, while ensuring regular realignment opportunities. This pattern resembles communication protocols used in human technology, where slight frequency offsets are deliberately introduced to prevent system lockup, while maintaining regular synchronization opportunities. The dust production patterns of 3I Atlas provide perhaps the richest source of potential encoded information. The object creates an asymmetric dust coma, with a distinctive forward-facing fan structure that changes systematically over time. These changes could represent natural responses to varying solar heating, but they could also constitute a form of optical communication visible across interstellar distances. The dust particles themselves carry information in their chemical composition and size distribution. Spectroscopic analysis reveals specific molecular signatures that could represent chemical encoding of information. Different isotopes and compounds scatter light at characteristic wavelengths, creating spectroscopic fingerprints that could be controlled to encode complex datasets. The temporal evolution of dust production shows patterns that suggest information content. The rate of dust ejection varies systematically over time, scales ranging from hours to weeks, creating complex temporal signatures that could represent encoded messages. These variations are too systematic to result from random outgassing processes, but they match patterns expected from controlled material release designed for communication purposes. Radio observations of 3I Atlas have detected emissions at frequencies that could represent both beacon signals and data transmission. The object produces signals at the hydrogen line frequency of 1420.4 MHz, one of the most fundamental frequencies in radio astronomy, and a natural choice for interstellar communication. This frequency would be immediately recognizable to any radio-capable civilization as an artificial signal rather than natural cosmic noise. The strength and stability of these radio emissions suggest active transmission rather than passive reflection of solar radio energy. The signals show frequency modulation patterns that could represent digital encoding, similar to techniques used in human communication systems. If these patterns indeed represent information transmission, they could contain vast amounts of data about 3I Atlas's mission, findings, and intended recipients. The polarization characteristics of radio signals from 3I Atlas provide additional encoding dimensions. The orientation of electromagnetic wave polarization can be controlled to encode binary information, with different polarization states representing digital ones and zeros. Natural radio sources typically produce unpolarized or randomly polarized emissions, but artificial transmitters can create sophisticated polarization patterns that represent complex data structures. The thermal signature of 3I Atlas reveals temperature patterns that don't correlate perfectly with solar illumination, suggesting possible internal heat sources or thermal management systems. These temperature variations could represent thermal encoding of information, with controlled heat distribution creating detectable infrared signatures that encode data about the object's internal systems and operational status. The gravitational effects of 3I Atlas, while too weak to measure directly, influence its dust production in subtle ways that could encode information. The object's gravitational field shapes the trajectories of ejected dust particles, creating distribution patterns that could be controlled to represent encoded data. By varying the density and composition of ejected material, the object could create gravitationally modulated signatures that carry information about its mass distribution and internal structure. The chemical composition of materials ejected by 3I Atlas could encode information at the molecular level. Different isotopic ratios and molecular structures could represent chemical encoding schemes that carry vast amounts of information in forms that would persist long after the object itself has departed our solar system. Future missions capable of collecting and analyzing these materials could potentially recover encoded information even decades after 3i Atlas has moved beyond detection range. The challenge of decoding potential messages from 3i Atlas parallels efforts to understand ancient human languages and writing systems. Archaeologists have successfully decoded Egyptian hieroglyphs, Mesopotamian cuneiform, and Maya glyphs by recognizing patterns, identifying recurring elements, and finding relationships between symbols and their probable meanings. Similar approaches might be applicable to alien communication systems, looking for mathematical relationships, recurring patterns, and correlations between different signal characteristics. The Rosetta Stone enabled decoding of Egyptian hieroglyphs because it contained the same information written in multiple scripts, including one that scholars could already read. In the case of 3i Atlas, the Rosetta Stone might be the physical properties and behaviors that can be understood through conventional physics, providing context for interpreting more sophisticated encoded information. Mathematical constants and physical relationships could serve as universal elements in any interstellar communication system. The ratio of a circle's circumference to its diameter, the fine structure constant that governs electromagnetic interactions, the mass ratios of fundamental particles, these values would be identical for any technological civilization regardless of their origin or development pathway. Alien messages might use these universal constants as reference points for encoding more complex information. The timing relationships between different aspects of 3i Atlas's behavior could represent temporal encoding of information. The correlation between rotation period, dust production cycles, and radio emission patterns might encode mathematical relationships or physical constants that would be immediately recognizable to scientifically advanced observers. These temporal patterns could serve as a cosmic Morse code, using time itself as the medium for information transmission. If successful decoding reveals that 3i Atlas is indeed transmitting information, the content of that message could be extraordinary. The object might be providing detailed scientific data about conditions in distant stellar systems, technological solutions to universal challenges, or even philosophical insights from civilizations with millions of years of experience. Such information could accelerate human development by millennia, while fundamentally transforming our understanding of intelligence and consciousness on cosmic scales. But the message might also contain warnings or restrictions about our future development. Advanced civilizations might use such communications to guide younger species away from dangerous technologies or destructive developmental pathways. The information encoded in 3i Atlas could include guidelines for responsible technological advancement, environmental stewardship, or peaceful coexistence with other intelligent species. The possibility that we are receiving and potentially decoding our first message from an alien intelligence represents one of the most significant moments in human history. Whether that message contains scientific data, philosophical insights, warnings about our future, or simply confirmation that we are not alone in the universe, its successful decoding would mark humanity's graduation from cosmic childhood to participation in a larger community of intelligent beings. The tools and techniques being developed to analyze 3i Atlas thus represent more than just astronomical research methods. They constitute humanity's first serious attempt to develop interstellar communication capabilities, preparing us for participation in conversations that span the galaxy and may have been ongoing for millions of years before our species ever gazed up at the stars. The scientific community's response to the communication hypothesis has been swift, divided, and increasingly intense. What began as speculation about unusual interstellar objects has evolved into a fundamental debate about the nature of intelligence in the universe and our methods for recognizing it. The stakes couldn't be higher. If we're wrong about natural explanations, we miss the greatest discovery in human history. If we're wrong about artificial origins, we risk undermining the credibility of scientific inquiry itself. Dr. Alan Fitzsimmons of Queen's University Belfast, one of the leading critics of artificial origin hypotheses, argues that the statistical sample is simply too small to draw meaningful conclusions about patterns or coordinated behavior. With only 3 confirmed interstellar objects, he contends, any apparent correlations between their properties or arrival times could easily result from selection bias and small number statistics. These ejection processes, operating across billions of stellar systems over galactic timescales, would populate interstellar space with vast numbers of wandering objects. Our recent detection of multiple interstellar visitors simply reflects the fact that our observational capabilities have finally reached the sensitivity threshold necessary to detect these objects regularly. From this perspective, the unusual properties of Oumuamua and 3i Atlas represent the extreme ends of natural variation rather than evidence of artificial construction. The compositional analysis of 3I Atlas strongly supports natural origin interpretations. The object's abundant water ice and organic compounds match theoretical predictions for comets formed in the outer regions of ancient stellar systems. Its spectroscopic properties are consistent with materials that have been altered by millions of years of exposure to cosmic radiation. Exactly what would be expected for an object that has wandered through interstellar space since shortly after its origin system's formation. The preservation of volatile materials through extended interstellar travel, while challenging to explain, doesn't require artificial protection mechanisms. Computer models show that objects larger than a few kilometers can retain internal ice reservoirs for millions of years if their surfaces develop protective crusts of non-volatile materials. The scale of 3I Atlas makes it particularly resistant to space weathering effects that would strip away volatile materials from smaller objects. However, proponents of the artificial hypothesis have developed increasingly sophisticated arguments that address these natural explanations, while highlighting aspects of the object's behavior that remain difficult to explain through conventional mechanisms. Dr. Avi Loeb's research group at Harvard has published detailed statistical analyses showing that the probability of both Oumuamua and 3I Atlas exhibiting their observed properties through purely natural processes is extraordinarily low when calculated independently. The artificial origin advocates point to several specific characteristics that challenge natural explanations. The precise trajectory alignment of both objects with our solar system's ecliptic plane represents a statistical anomaly that becomes more significant when considered together rather than separately. The timing of their arrivals, coinciding with critical periods in human technological development, strains credibility as mere coincidence. More technically, the advocates argue that the acceleration mechanisms proposed for Oumuamua require special pleading about material properties and formation environments that have never been observed elsewhere. The hydrogen ice hypothesis demands that the object consist of materials so pure and unusual that they would be unlikely to form through natural processes. The debate has been complicated by the involvement of public and media attention that often emphasizes sensational aspects while overlooking technical details. Popular coverage has sometimes portrayed the artificial hypothesis as more widely accepted than it actually is within the professional astronomical community, creating public expectations that may not align with scientific evidence. This media dynamic has created pressure on researchers to take definitive positions on questions that may not yet have definitive answers. Scientists advocating for continued investigation of artificial possibilities risk being dismissed as sensationalists, while those maintaining natural interpretations risk being seen as close-minded to revolutionary possibilities. The philosophical implications of the debate extend beyond astronomy into fundamental questions about intelligence, consciousness, and our cosmic perspective. If artificial objects are indeed visiting our solar system, it forces us to confront the possibility that intelligence may be common in the universe, and that we may be far from the most advanced technological civilization in our galactic neighborhood. Conversely, if these objects prove to be natural, they provide unprecedented opportunities to study materials from distant stellar systems and understand processes that govern galactic evolution. The scientific value of either interpretation is enormous, but the implications for humanity's future development are radically different. The debate has also highlighted tensions within the scientific community about appropriate responses to extraordinary claims. The principle that extraordinary claims require extraordinary evidence is fundamental to scientific methodology, but determining what constitutes extraordinary evidence for potential alien artifacts remains contentious. Some researchers argue that the current observational data, while intriguing, falls far short of the evidence needed to support artificial origin claims. They contend that natural explanations, while sometimes requiring unusual circumstances, remain more plausible than invoking alien technology. Others argue that the potential significance of alien visitation justifies serious investigation of artificial possibilities even when natural explanations remain viable. They contend that the cost of missing evidence of extraterrestrial intelligence far outweighs the risk of pursuing hypotheses that ultimately prove incorrect. From this perspective, the artificial hypothesis deserves continued attention until definitively ruled out by observational evidence. The debate has practical implications for future research priorities and funding decisions. Resources devoted to investigating artificial possibilities are resources not available for other astronomical research. However, the potential payoff from confirming alien visitation would justify enormous investments in specialized observation and analysis capabilities. International space agencies have begun developing response protocols for scenarios involving confirmed artificial objects in our solar system. These protocols address everything from communication attempts and sample collection missions to information security and public announcement procedures. The mere existence of such planning documents reflects the growing recognition that artificial visitation represents a genuine possibility that requires serious preparation. The scientific instruments and techniques being developed to study interstellar objects also serve broader astronomical research goals. Improved spectroscopic capabilities, enhanced trajectory determination methods, and sophisticated pattern recognition algorithms benefit multiple areas of astronomy, regardless of whether they ultimately confirm natural or artificial origins for specific objects. As Three-Eyed Atlas continues its passage through our solar system, the debate between natural and artificial interpretations intensifies with each new observation. The object's behavior during its closest approach to the Sun, when thermal stresses and radiation environments reach peak levels, may provide definitive evidence about its nature. Natural objects would be expected to show increased activity and possible fragmentation under these extreme conditions, while artificial objects might exhibit controlled responses or protective behaviors. The resolution of this debate will likely require observations that go beyond what Earth-based telescopes can provide. Future intercept missions capable of close-up imaging and sample collection could provide the definitive evidence needed to distinguish between natural objects and potential artifacts. Such missions represent enormous technical challenges, but the potential scientific return justifies the investment required to attempt them. Whether the debate ultimately supports natural or artificial interpretations, it has already transformed our approach to studying interstellar objects and our perspective on the possibility of extraterrestrial intelligence. The questions raised by Oumuamua and Three-Eyed Atlas have forced astronomy to develop new theoretical frameworks, observational techniques, and analytical methods that will serve the field for decades to come. The intensity of the debate reflects its significance for humanity's understanding of our cosmic context. We stand at a unique moment in our species' development, where our technological capabilities have reached the threshold necessary to detect and analyze potential evidence of alien intelligence. How we handle this opportunity may determine whether future generations look back on this period as the beginning of humanity's integration into galactic civilization, or as a missed opportunity to recognize evidence that was hiding in plain sight. If the communication hypothesis proves correct, if Oumuamua truly summoned Three-Eyed Atlas through an interstellar signal network, then humanity stands at the threshold of the most profound transformation in our species' history. We would no longer be alone in the universe. We would no longer be the only known intelligence in the cosmos. And most significantly, we would discover that we have been under observation by advanced civilizations for far longer than we ever imagined. The implications cascade across every aspect of human civilization: our technology, our philosophy, our understanding of our place in the universe, our responsibilities as a species. Everything would be fundamentally altered by confirmed contact with alien intelligence, even if that contact remains indirect and mediated through physical messengers rather than direct communication. From a technological perspective, confirmed artificial origin for these interstellar objects would represent proof that interstellar travel is not only possible, but has been achieved by civilizations capable of deploying massive objects across galactic distances. The engineering required to construct 11-kilometer artificial objects, accelerate them to interstellar velocities, and guide them across light years with precision that enables arrival at predetermined times would demonstrate technological capabilities that dwarf anything in human experience. Such capabilities would imply mastery of energy sources orders of magnitude beyond our current reach. Stellar-scale engineering projects that could harness the entire energy output of stars for massive construction and propulsion systems. Materials science advances that enable structures to survive millions of years in the harsh environment of interstellar space, while maintaining complex functionality. Navigation and guidance systems capable of course corrections across distances and timescales that challenge human comprehension. But technological implications represent only the beginning of the transformation that confirmed alien contact would trigger. The philosophical impact would be equally profound, forcing us to reconceptualize our understanding of intelligence, consciousness, and our role in the cosmic order. For most of human history, we have assumed that Earth represents the center of meaningful existence in the universe. Even after accepting that our planet orbits an ordinary star in an unremarkable galaxy, we have maintained the assumption that intelligence and consciousness are rare cosmic phenomena, possibly unique to our own evolutionary lineage. Confirmed alien intelligence would shatter this anthropocentric worldview. We would discover that intelligence is not rare, but possibly common throughout the galaxy. We would learn that consciousness and technological capability can emerge through evolutionary pathways very different from our own. We would confront the reality that our entire recorded history represents barely a moment in the development of galactic civilization. This philosophical transformation would ripple through every human institution and belief system. Religions would need to incorporate the reality of non-human intelligence into their theological frameworks. Educational systems would need to teach cosmic perspectives that place human achievement in galactic context. Political systems would need to address humanity's responsibilities as members of a larger community of intelligent species. The economic implications would be equally transformative. Technologies derived from studying alien artifacts could revolutionize human industry and energy production. Scientific information transmitted by alien messengers could accelerate our understanding of fundamental physics by centuries or millennia. The mere knowledge that interstellar travel is achievable could motivate investments in space exploration that would transform our species into a spacefaring civilization. But the benefits would come with corresponding challenges and responsibilities. Confirmed contact with alien intelligence would raise questions about our readiness for such contact, and our worthiness as participants in galactic civilization. Advanced civilizations observing our behavior might judge us based on how we treat our own planet, how we resolve conflicts between nations, and how we manage the risks and benefits of our own technological development. Our response to the discovery of alien intelligence would itself be observed and evaluated. Panic, military mobilization, or attempts to weaponize alien technology might be interpreted as evidence that humanity is not ready for broader contact. Conversely, measured scientific investigation, international cooperation, and peaceful response might be seen as positive indicators of our maturity as a species. The communication protocols we develop for potential interaction with alien intelligence would need to account for vast differences in technological capability, temporal perspective, and possibly even basic physics understanding. The security implications of confirmed alien contact would also be enormous. Knowledge that advanced civilizations possess technologies capable of interstellar travel would force reassessment of national defense priorities and international cooperation mechanisms. The possibility that such civilizations might have different intentions or moral frameworks than humans would require unprecedented levels of global coordination to manage potential risks and opportunities. Educational systems would face the challenge of preparing human minds for a universe filled with intelligence, vastly more advanced than our own. Current educational approaches, which often emphasize human achievement and technological progress, would need to be balanced with cosmic perspectives that place our accomplishments in proper galactic context, without undermining human confidence and motivation. The psychological impact on individual humans could be equally profound. Discovering that we are not alone in the universe would trigger a range of emotional responses from excitement and wonder to anxiety and existential uncertainty. Mental health systems would need to prepare for helping people process the implications of confirmed alien intelligence and integrate these revelations into their personal worldviews. The timeline for these transformations would likely extend across generations rather than years. The full implications of confirmed alien contact would unfold gradually as we develop better understanding of the intelligence we've encountered and learn to interpret their communications more effectively. Each new interstellar visitor might bring additional information that deepens our understanding of galactic civilization and our place within it. The response protocols being developed by space agencies and international organizations reflect growing recognition that such contact scenarios require serious preparation. These protocols address issues ranging from initial confirmation procedures and information verification to public announcement strategies and long-term relationship management with alien intelligences. But perhaps the most significant implication involves our responsibility to future generations. If we are indeed receiving communications from alien intelligence through objects like 3i Atlas, then our response will determine how humanity's relationship with galactic civilization develops over the coming centuries. The choices we make about investigation priorities, international cooperation, and technological development could influence whether our species becomes a respected member of the galactic community or remains under passive observation as a potentially dangerous developing civilization. The emergence of citizen science projects focused on interstellar object research also reflects changing public engagement with these possibilities. Amateur astronomers and volunteer researchers are contributing to data analysis and hypothesis development in ways that would have been impossible during earlier eras of astronomical research. This democratization of investigation could help ensure that the search for evidence of alien intelligence reflects humanity's collective interests rather than the perspectives of small groups of professional researchers. The long-term implications of the communication hypothesis extend to humanity's cosmic destiny. If we are indeed part of a galaxy filled with intelligence, then our future development might be guided by access to knowledge and technologies accumulated by civilizations with millions of years of experience. We might avoid the dangers and dead ends that could otherwise derail our technological progress while accelerating our advancement toward capabilities that enable meaningful participation in galactic civilization. Conversely, if we misinterpret natural phenomena as evidence of alien intelligence, we risk pursuing costly investigations that divert resources from more productive research directions. The opportunity costs of focusing on artificial origin hypotheses could slow our legitimate scientific progress and technological development. The resolution of these questions will likely define the next phase of human development as a technological species. Whether we discover that we are alone in a universe of natural phenomena or part of a galactic community of intelligent beings will shape our priorities, our investments, and our understanding of what it means to be human in an age of cosmic awareness. As 3i Atlas continues its journey through our solar system, humanity finds itself poised between these radically different futures. The next few months of observations may provide the evidence needed to distinguish between natural and artificial interpretations, potentially marking the beginning of our species' transition from cosmic childhood to galactic citizenship. As 3i Atlas begins its slow departure from our solar system, fading gradually from our telescope's view like a cosmic ship disappearing over the horizon, we find ourselves forever changed by its passage. Whether this massive visitor represented a natural wonder from the depths of space, or our first confirmed response from an alien intelligence, its impact on human consciousness has been profound and irreversible. The evidence we have gathered paints a picture that is simultaneously compelling and incomplete. 2 objects arriving from interstellar space within 8 years, both exhibiting properties that challenge natural explanations, following trajectories that seem almost perfectly designed for Earth observation. The timing correlation suggests a cause and effect relationship that transcends mere coincidence. The scale progression from scout-sized to battleship-sized visitors implies escalating contact protocols rather than random encounters. Yet science demands rigorous skepticism and natural explanations for these phenomena, while sometimes requiring unusual circumstances, remain scientifically viable. The composition of 3i Atlas matches what we might expect from ancient cometary materials. Its behavior, while remarkable, can be modeled using conventional physics applied to extreme but not impossible conditions. The apparent patterns in arrival timing and trajectory correlation could represent selection bias in our small observational sample. But perhaps the most significant outcome of this cosmic encounter isn't the resolution of the natural versus artificial debate. Perhaps it's the transformation of human awareness that comes from seriously contemplating these possibilities for the first time in our species' history. We have learned to scan the skies not just for random cosmic phenomena, but for potential evidence of intelligence operating on scales that dwarf human experience. We have developed analytical frameworks capable of distinguishing between natural processes and possible artificial construction. We have begun to think seriously about our responsibilities as a technological species in a universe that might be filled with civilizations far more advanced than our own. The infrastructure we've built to study interstellar objects, the automated survey systems, the coordinated international observation networks, the sophisticated analytical algorithms, represents humanity's first serious attempt to monitor our cosmic environment for signs of intelligence. This infrastructure will continue operating long after 3i Atlas has faded from view, ready to detect and analyze whatever visitors the galaxy might send our way next. And there will be more visitors. The success of our detection systems virtually guarantees that additional interstellar objects will be discovered in the coming years. The Vera C. Rubin Observatory, when fully operational, could detect dozens of such objects annually. Each new detection will add to our statistical sample, potentially revealing patterns that support either natural or artificial interpretations. The next interstellar visitor might arrive with properties that definitively resolve the debate about alien intelligence. It might exhibit obviously artificial characteristics that cannot be explained through any natural mechanism. It might transmit clearly structured signals that represent unambiguous attempts at communication. It might even attempt direct interaction with human spacecraft or installations, removing any doubt about its artificial nature. As we stand beneath the night sky, watching for the next visitor from beyond our solar system, we carry with us the knowledge that we may no longer be alone. Every point of light moving against the stellar background could be another messenger carrying news from distant civilizations. The universe around us, once thought to be filled primarily with dead matter and empty space, might actually teem with intelligence, operating on scales we are only beginning to comprehend. Networks of artificial objects might be carrying information between civilizations throughout the galaxy, following protocols established millions of years before our species evolved. The capacity to look up at the stars and wonder what might be looking back. In the cosmic ocean that surrounds our small solar system, we have learned to recognize the signs that might indicate artificial navigation rather than natural drift. We have developed the instruments and techniques necessary to study these visitors in unprecedented detail. We have prepared ourselves as much as any species can for the possibility that the next signal we detect might carry greetings from intelligences beyond our world. The call may already have been answered. The message may already have been delivered, and somewhere in the darkness between the stars, the next chapter of this cosmic conversation may already be approaching, carrying with it revelations that will transform our understanding of intelligence, consciousness, and our destiny as a species awakening to its place in the galactic community. Until that next signal arrives, we wait and we watch, and we listen, knowing that the universe has become a far more interesting and potentially populated place than we ever dared to imagine. The age of cosmic loneliness may be ending, replaced by an era of galactic awareness that will define the future of human civilization among the stars. The conversation continues. The signals persist, and humanity listens with new ears to the cosmic symphony playing out in the darkness above our heads, alert for the next movement in what might be the grandest composition ever written across the stars themselves.